We'll be looking at lesson 2.02 today. Shh, please be discreet. Notice this is the discrete we talked about last week versus the math discrete. So today's objective is, given a relationship, I can correctly choose discrete or continuous and write the domain in 2 out of 2 problems. Those are vocabulary words from last week. So can you think to yourself, what did discrete mean? What did continuous mean? And what was the domain? Here's some things to think about. What is the difference between discrete and continuous functions? And how can I tell them apart in context? So we talked last week about discrete being points that it didn't make sense to connect together. These are discrete. We also thought of them as countable, but not measurable. Versus continuous, which it does make sense to connect. So we draw those dots, but then we could connect them. And these tend to be measurable, but not countable. And then another thing to think about is, how is domain related to whether a function is discrete or continuous? Now, if you don't remember what domain is, that's okay. We're going to go over it again today. But think about how it relates to the continuity of the function. So today we're going to talk about the Library of Congress. This is the super cool giant library in Washington, D.C. And the Library of Congress is considered the largest library in the world. That just looks amazing to me. I could go in there and just be a happy camper forever. They often receive boxes of books to be added to their collection. And since books can be quite heavy, they really only put a few books in each box. On average, each box contains 8 books. If you've ever moved before or packed up a bookshelf or something like that, you'll notice that boxes of books can be quite heavy, and so it makes sense to limit the size of these boxes so that they can be reasonably shipped. So this looks like problems we're used to. If on average each box contains 8 books, how many books does the library receive in 6 boxes, in 10 boxes, or in n boxes? How do we figure that out? Well, let's see. If we have 6 boxes and we have 8 books per box, notice this is similar to those ratio problems we did last week on the assignment. We can cancel out boxes, and we're going to be left with books as our unit. 6 times 8 is 48 books. So that's how many books we'd have in 6 boxes. We could do a similar thing with 10 boxes. So we could do 10 boxes times 8 books per box, and we would get 80 books. Or if we don't know the number of boxes, we just have n, we could say n boxes times 8 books per box equals n times 8, or we often write this 8n. So really that's just our equation, because if we look over here and say we have boxes and books, we could number these up, 0, 1, 2, 3, 4. We know that 0 boxes would have 0 books. 1 would have 8, because there are 8 books per box. We add 8 there. 2 boxes would have 16, so we're adding 8 each time. We can see our common difference is 8, and our value at 0 is 0. So our equation is going to be f of n equals common difference times the variable plus the value at 0. Now 0 plus 0 doesn't really do anything, so we can just kind of cross that out, right? So our overall equation here is, got that kind of messed up. Let's just delete that. Our overall equation here is f of n equals 8n. Now instead of graphing this by hand, we have talked about how to graph this by hand, but I used Desmos and made a nice clear graph. And you can see here we go up 0, 0, we go up 8 books for 1 box, then to 16, then to 24, and so on. And the question is this a linear or exponential function? Now we kind of equated linear and arithmetic, exponential and geometric. So if you can identify what type of sequence it is, you can determine what the shape of the graph should be. You can also just look at the graph. Is this a curve or a straight line? Since it has a common difference, and because it's a straight line, we call this linear. Notice that the word linear has the word line in it. It means it makes a straight line. Exponential, we'd expect it to be more like a curve like that, or possibly like this. Is this discrete or continuous? What do you think? Does this go up in chunks, or could we draw a line that makes sense? If we drew a line here between these two dots like that, we'll pretend that's a straight line. And I looked at a point right there. We might say that is half a box and like 4 books. Does half a box make sense? Or we could even do something a little bit weirder and over here, and this would be like half a book. Does half a book make sense? Can you ship half a book? If you have half a box, it's still a box, right? You can cut a box in half and then it is a box. So there isn't really such thing as half a box. And likewise, shipping half a book, we don't even know what that means. Like if you tear a book in half, is that going to be half a book? I mean, it's still a book. It's still a whole book. It just is missing part of it. So we don't ship half books. We don't ship half boxes. This is a discrete function because the lines in between here don't make sense. We're going to delete all this stuff because none of it makes sense. This line in between, the only part that makes sense are the parts where we have the dots. So this is a discrete function. And then what is the domain? Let's remind ourselves what the domain meant. So we were talking about valid input values. So what are the valid input values here? Is -1 valid? Can we ship -1 boxes? How about 0 or 1? How about 1/2? Is 1/2 a valid input? So we already discussed this 1/2. 1/2 of a box doesn't make sense. We don't know what that is. All these numbers in between 0 and 1 don't make sense. -1 doesn't make sense. We can't ship a negative box. We don't even know what that means. So it looks like our valid input values here are 0, 1, 2, 3, and so on. And we can write those as a list just like this, 0, 1, 2, 3, ... Now we do have a fancy way of writing domain that we're going to introduce today. So this is the normal way. Usually when we write sets of numbers, we'll put them in these curly brackets. But we can use something fancy called set builder notation. This is very common notation in mathematics to define sets of numbers. So here's what this looks like. We're going to have our same old curly brackets, and now we're going to have a variable. We just define a variable. We have this character, it's a vertical line, it's called a pipe, and you can type that on your keyboard. It's usually a key above your enter key, and you'll need to press shift on that one. So you get a backslash without the shift, and then it's the pipe with the shift. And then some condition that x satisfies. It could even be more than one condition. So we read this x such that x is greater than 5 in this case. So that's what this pipe means. This pipe means the word such that. X such that x is greater than 5. So here's some examples of set builder notation. You can just use words. N is an odd integer. That would work. N such that n is an odd integer. Or a such that -2 is less than or equal to a is less than or equal to 2. or t, such that t is an integer where t is greater than 0. Now this is very similar to the one we were just looking at in that problem. T is greater than or equal to 0 would have been what we'd use for that problem. So we scroll way back up here and want to write this one in set builder notation. We would write curly bracket, no, write an actual curly bracket. There we go. X such that X is an integer and X is greater than or equal to 0. Then close the curly bracket. So you see we can have two conditions in there. We can have more. We can have one condition. We could have a list of numbers. Anything that describes the set of numbers would work in here. The trick is just putting the variable, little pipe, and putting the brackets around it. Let's look at another example. So many of the books at the Library of Congress are electronic. About 13 ebooks can be downloaded onto the computer each hour. Okay, so we're downloading ebooks. If about 13 ebooks can be downloaded each hour, how many ebooks can be added to the library in 3 hours, 5 hours, or n hours? Well, we should be able to use a similar method here. Let's see, we have 13 books per hour. We can multiply that by 3 hours over 1. Our hours are going to cancel. We're going to get books as our units, and we'll get 13 times 3 equals 39 books in 3 hours. So if I write out my table over here, we have hours and books, and I can list out my hours, and we just calculated 3 to be 39. About 5 hours. It asks for 5 hours. Well, we use the same method. 13 times 5. Let's see, that's going to be 65, I think. 65 books. Now, I didn't write out the units that time, but they would be exactly the same. 13 books per hour times 5 hours over 1. The hours would cancel, we'd get books. So if we had a 5 down here, it would be 65. If we had 0 hours, that would be 0 books clearly. 13 books per hour means we could do 13 in 1 hour. 26, because we're just adding 13 each time, right? Each hour we get 13 more books. 39 plus 13 is 52, and then 65. So what is our equation here? Remember, we're looking for the common difference, which is 13, and then our value at 0, which is 0. So our equation is going to be mx plus b, where m is our common difference. Oh, but we want n, because that's the variable we used. And then b is our value at 0. 13n plus 0. Remember, plus 0 doesn't mean anything, doesn't add anything, so we could just do 13n. That could be our equation. Once again, I'm not going to graph this by hand. We can just look at it in Desmos. Is this linear or exponential? What do you think? Well, this is arithmetic. We're adding, so linear. Is this one discrete or continuous? Well, this is a little more interesting. Can ebooks be divided up? Would it make sense to have downloaded half an ebook? How about half an hour? In half an hour, could we have downloaded 6.5 ebooks? What do you think? Well, ebooks do kind of flow in continually, right? We download bytes continually. So 6.5 ebooks is actually a thing. We do download portions of books, and time is always continuous. Half an hour makes sense, quarter of an hour, 16 seconds. You can keep dividing up time as small as you want. Time is continuous. The flow of data on ebooks is continuous, so since both of our variables are continuous, this is a continuous function. And then what is the domain? Well, let's see, negative numbers don't make sense because there's no such thing as -2 hours that we've been downloading stuff. So 0 is a valid one. We said 1/2 is. 1 is. All of these numbers in between 1 and 2, between 0 and 1. So actually everything from 0 up is valid. So if we wanted to write that in set builder notation, it would look like this. Curly bracket x such that x is greater than or equal to 0. Now notice this time we didn't have to say x is an integer because we want to include numbers that aren't integers. We want to include the fractions in between the integers. So we just say x is greater than or equal to 0, and that will include all of them. Another example. The librarians work to keep the library orderly and put books back into their proper places after they have been used. A librarian can sort and shelve 3 books in a minute on average. Okay, so 3 books per minute. How many books can they shelve in 3 hours, 5 hours, or n hours? Okay, so it looks like we have hours and books shelved. Well, let's see, we could try our old method, 3 books per minute times 3 hours, but 3 hours over 1, none of our units cancel here. Darn, we need to add some other conversion. It looks like we've got some extra hours and some extra minutes. So how do we relate hours to minutes? We need a ratio to get rid of those. Well, we know that there are 60 minutes in an hour, so what if we did 60 minutes over 1 hour? Then our minutes would cancel, our hours would cancel, and we're left with just books. So we get 3 times 3 times 60. Let me put that in my calculator. 3 times 3 times 60 is, I get 540 books. So this one we had to do kind of a tricky thing where we converted from minutes to hours. So let's see, 0, 1, 2, 3, 4. 3 hours would be 540 books. How about 0? At 0 hours, obviously, they've shelved 0 books. How many could they do in 1 hour? Well, let's see. It'd be just like this previous one, 3 books per minute times 1 hour times 60 minutes per 1 hour. Our minutes cancel, our hours cancel, and we get 3 times 60 equals 180 books in 1 hour. So you can see we're still just adding 180 here. Even though we had that extra step, we can just add 180 each time. And that is our common difference. 540 plus 180 is 720. And then what is our equation? We have g of n equals the common difference times our variable plus the value at 0. There's our value at 0, there's our common difference. Plus 0 doesn't really do anything, so we can just say our equation here is 180n. Now, once again, I'm not going to graph this by hand. I'll just use Desmos. This is what our graph looks like. And here's a question, is this linear or exponential? Well, let's see, we know it's arithmetic. We saw it was mx plus b. We know this is a linear one. This is a straight line. You can even see that on the graph, straight line. Is it discrete or continuous? Oh, well, this is kind of an interesting question. What do you think? Is this discrete or continuous? Can you have half a minute? Can you have half a book? Can you shelve half a book? So half a minute actually makes sense. This is a continuous variable. But half a book, you can't shelve half a book. So because one of our variables is continuous and one is discrete, that means our function overall has to be discrete, because if it's not continuous anywhere, it can't be continuous over the whole thing. This is going to be a discrete function, even though we have time on the x-axis. Even though time is continuous, books are discrete. Books are countable. So here's another kind of tricky question. What is the domain on this one? What do you think? Well, we've determined that 0, 1, 2, these all have valid dots on them, so those are definitely part of them, part of our domain. Does -1 make sense? We can't really have -1 hours that we've been reshelving, so that doesn't make sense. But we did say that half a minute is possibility. So here's the question. Is our domain integers greater than 0, greater than or equal to 0? Is it all numbers greater than or equal to 0? Or is it some subset? What do you think? Well, let's actually, to answer this, let's expand out this graph. Let's draw a little bit bigger. So I'm going to draw my axes here. Here's my x-axis. Here's my y-axis. We'll pretend that's a straight line. And I'm going to draw my minutes out really big. I'm going to do 1, 2, 3, 4, 5, 6. And this is minute 1. 1, 2, 3, 4, 5, 6. This is minute 2. So these are each 10 seconds. 10, 20, 30, 40, 50, 60 seconds. And then 60 seconds here. So each one of these is 10 seconds. And then I'll draw my books like this, not because we can have half books, but just because I want them spread out a little bit. So just every 2 lines is a book. Oh, except I skipped a line on 3. There we go. 3 here, 4, 5. Okay. So we know that at 1 minute they've shelved 3 books. But at some point it seems like they would have shelved 2 books or 1 book, right? In fact, that would be 1 minute divided by 3, which would be 20 seconds. At 20 seconds they've shelved 1 book. At 40 seconds they've shelved 2 books. And then this pattern continues. A minute 20, they've shelved 4, then 5 at a minute 40, and so on. You can see we've zoomed in this graph. We still have a straight line between these dots. We'd still call it discrete, but we have more dots than we had before. We have a dot at 1/3 of a minute, at 2/3, at 1, at 1 and 1/3, at 1 and 2/3. All of those are valid dots, but none of the dots in between are valid. So our domain here is going to be increasing by thirds. 0, 1/3, 2/3, 1, 1 and 1/3. And we can write that in set builder notation like this. X such that 0, 1/3, 2/3, 1, 1 and 1/3, and so on. So we're going to skip this last problem and just go right back to today's objective. Given a relationship, I can correctly choose discrete or continuous and write the domain in 2 out of 2 problems. So all ones we looked at today were linear, but we identified different discrete and continuous based on the continuity of the variables involved. And then we also introduced set notation for domains, set builder notation.